Hi, good morning. This is Jagdish, Assistant Professor of EC Department, SNS College of Technology, Coimbatore. Today, in our video lecture series, we are going to discuss about the turn on and the turn off characteristics of a device. Come, let's get into the topic. So, the turn on and turn off characteristics of the device. The dynamic characteristic aims at assessing the switching behavior of power semiconductors to support the design and optimization of power electronic converters. Thus, the methodology for dynamic characterization should be simple and generic and conducted prior to the converter prototyping. An example is the voltage source inverter fed motor drive, which is typical representative of voltage source converter in the industrial applications. So as shown in the previous figure, the inverter consists of three phase legs. For each phase leg, it consists of two series connected power semiconductor switches with a DC voltage source across the lower and upper terminal and AC current source through its midpoint. It is worthwhile to notice that the freewheeling diode symbol illustrated in the figure can be physically be the body diode of the MOSFET, external pin or Schottky diode anti-parallel with the active device or diode-like behavior mechanism of gallium nitride FET. So this is the PWM voltage source inverter FET motor drive uh, circuit construction. And here there is a PWM, that's a pulse width modulation control signal for upper and lower switches. This figure illustrates that the typical pulse width modulation (PWM) control signals of lower and upper switches in the phase leg. These two signals are complementary with the dead time embedded to avoid short circuit of DC voltage source. The symmetry of three phase legs and their similar switching commutation, only one phase leg is focused on in the following description. Regarding the motor load as AC current source, there are two scenarios. One is the inductive load current flowing in the midpoint of the phase leg. The other is inductive load current flowing out of it. So there are three cases. First one T0 to T1, and then T1 to T2, and T2 to T3, and T3 to T4. So T0 to T1, both the lower and upper switches are off. During this time, the load current flows through the freewheeling diode of the upper switch, and T1 to T2, the lower switch turn on, and the load current commutates from the upper diode to the lower switch, while the DC voltage shift to the upper diode from the lower switch. Thus, the hot turn on switching commutation occurs between the upper diode and lower switch. T2 to T3, lower switch turns off. The load current commutates from the lower switch to the upper diode, while the DC voltage shifts to the lower switch from the upper diode. T2 to T3 to T4, upper switch turns on. Before the turn on of the upper switch, the load current already flows through its freewheeling diode. Turn on of their upper switch only offers another current path in the parallel with the upper diode. If the switch is capable of conducting reverse current, the impedance of this current path offered by the switch channel may be lower than the impedance of its freewheeling diode, as in the case of WBG devices. This turn-on transition only transfers the load current out of all depending on the impedance ratio from the upper diode to the upper switch when both devices are under zero voltage. There is no hard switching commutation between the upper and lower switches. This termed as the synchronous turn-on and the commutation, and the no hard switching commutation loss exists. So T4 to T5, upper switch turns off, similar to the aforementioned analysis of for T3 to T4. During this turn off transition, the load current transfers from the upper switch back to the upper diode. As a result, there is no hard turn off switching commutation along with its associated turn off switching energy loss. This is called synchronous turn off commutation, switching commutation. So the four cases are given over here. Consider the case of load current flowing out of the midpoint of the phase leg as shown in the previous figure. T0 to T1, both the lower and upper switches are turned off. During that time, the load current flows through the freewheeling diode of the lower switch. T1 to T2, lower switch turns on. The load current transfers from the lower diode to the lower switch. This is a synchronous turn-on switching commutation. And T2 to T3, lower switch turns off. The load current transfers from the lower switch back to lower side, lower diode. This is a synchronous turn-off switching commutation. T4 to T5, upper switch turns off. Load current commutates from the upper switch to the lower diode. This is also a hard turn off switching commutation between the lower and the upper switch. In the summary, when the load current flows out of the midpoint of the phase leg, the hard switching commutation only occurs between the lower diode and the upper switch. The lower switch in this case behaves as a synchronous switch. Thank you.